Okay, so in problem 2-84, we're giving this contraption, this figure right here, and we have to determine the magnitude of the projected component of F along AC, and we have to express that component as a Cartesian vector. Okay, so thinking about how we're going to solve this. We have an A and a B and a C point, which means we can make a couple vectors here from these points. Excuse me as I shift my grip on the camera. So we can make a couple vectors here. And then we also have this force vector, 30i minus 45j plus 50k. And I see that we have to find a projected component of F along AC, which really all that means is it wants you to take the dot product of the force and whatever vector they give you. So we're just going to dot F and AC to find this. So in order to dot two vectors, we need to have two vectors. So we have to find AC. So I went ahead and I just found A, B, and C just for completeness, which for A I ended up getting 0, 0, 0, because that's at the origin. B's 3, 4, 0, and C is 7, 6, negative 4. Alright, so from there we can go ahead and find AC. And if you don't know how to find a vector, it's the second, let me think how to word this. It is the second coordinate minus the first coordinate. So the C coordinates minus the A coordinate. So going over to my work here, we have our A, B, and C positions right there. So our AC vector is going to be 7 minus 0 to give 7i. 6 minus 0 to give 6j, and then negative 4 minus 0 to give negative 4k. So we have our AC right there. Okay, so now what we're going to do is we're going to find the magnitude of AC, because in order to project that force we need to have a unit vector AC. In order to find a unit vector, you simply just need to divide a vector by its magnitude, and the magnitude of a vector is given by the square root of the sum of the squares of the components. So for our case in AC, the magnitude is going to be the square root of 7 squared plus 6 squared plus negative 4 squared. You're going to end up with the square root of 101 feet, and your unit vector in AC is going to be 7i plus 6j minus 4k divided by the square root of 101. Okay, so going back to the problem here, we have our F vector, our force vector, we have our unit vector in AC, so now we are ready to dot this. So dotting two vectors, the dot product, is simply just multiplying the two x's, the two y's, the two j's, and adding them all together. Multiplying the two x's, the two y's, and the two z's, and then adding all those together. Don't have to worry about directions because dot products give scalars. So to find the force along AC, it's going to be as simple as 30, which is the I component of our vector, times 7 over the square root of 101, and then negative 45 times 6 over the square root of 101, and then 50 times negative 4 over the square root of 101. That's going to end up giving us negative 25.87 pounds. Okay, so we found our projection of F along AC, but they want it as a Cartesian vector. So we found F along AC, but we haven't actually found the Cartesian vector F along AC. All we did is we found the magnitude of the force along AC, but we haven't actually found the individual components. So we have the magnitude, which as I said was negative 25.87, or rather 25.87 because it's a magnitude. Or no, excuse me, you are going to need a negative because that gives directions. So it is negative 25.87 pounds along AC. In order to find the Cartesian vector of F along AC, you are just going to multiply F by your unit vector again. So as shown over here, negative 25.87 pounds times over here is your unit vector of AC. It's the same exact vector right here. So when you multiply all that out, you're going to end up with negative 18.02I minus 15.44J plus 10.3K pounds. And that is your component of F along AC. And that's all they ask for, so we're done with the problem.